So once it's solved and the progress bar at the bottom disappears, it'll come up with a window that says something like solution complete or something along those lines. At which point we can go ahead and analyze what the solution sort of told us. So the first thing we're probably going to want to do, and that's the main thing I guess most people are concerned with, is going to be what forces does our rear wing produce, right? So let's go ahead and find out. Remember we made that report definition. So if we double click on report definitions, we made that drag report definition. So if we click that and then click compute, you might think nothing happens. If you then go to the console, you will now see it has computed the drag value of our rear wing. So after solving 150 iterations of the flow around that rear wing, it told us that it's producing 122.938 newtons of drag at 22.22 meters per second. Remember, this is only half of the wing. So we actually want to double this for our full rear wing. So it's actually producing somewhere around 245 or 246 newtons of drag at this speed. From there, we can calculate CL and CD pretty easily because we have the velocity, we have the density, we have our reference area, and it becomes very easy if you just follow the equation. But this is a very simple method to just calculate the force itself. There are other ways we can do this. If we go ahead and close this task page, there's other ways we can calculate the drag on our part. We don't have to have a report definition. We scroll down to reports and open up forces, double click on forces. This doesn't specify whether drag, lift, etc. But if you specify the force and in which direction, so X is our drag, and we select all of the faces we wanted to calculate the drag for, and then we hit print, there's a very similar thing, except with a lot more detail. So it'll show you how much drag each component is actually producing of the rear wing. And the total, of course, is identical as what the report said. But this is actually a good breakdown. So we know that element 1 is producing 35, element 2 is producing 55 newtons of drag, element 3, 30, and all of these others are minimal. So this is, I guess, more in-depth view. It's the sum of the pressure and the viscous drag. So pressure drag obviously is induced by the pressure created from the flow, whereas the viscous drag is the actual friction that the airflow experiences on the surface of the rear wing. You can see that's very, very minimal for our rear wing. It's going to be minimal for the entire car because we're not going at crazy speeds. We don't have ultra rough surfaces, and the airflow isn't that viscous. So this is always going to be very, very small. But the total, of course, matches. Now, if we want to check for lift, we know the lift direction is the Y. So if we put 1 and 0 instead and print, we can see how much lift it's producing. Obviously, it's negative because it's producing downforce, which is a good sign. And remember, this is half. So if we double it, we're producing somewhere around 601 newtons of downforce at 80 kilometers an hour. So that's the way you find out forces. Now, forces isn't the only thing we want. So we want to check if our simulation was any good, right? So how do we trust that the simulation was effective? Well, there's no way to really tell except if you put it through a wind tunnel or actually test it on track and get these same values. But there is a way we can simulate whether we can check whether the simulation was good by seeing if the airflow into the simulation is roughly equal to the airflow out of the simulation, right? So inlet minus outlet should be roughly 0. And we can do that if we go to double-click fluxes and mass flow rate. If we then select inlet and outlet, it'll give us a net result. So we'll compute, and our net result is e to the minus 5, which is very, very small. Anything below e to the 3, e to the 4 is perfectly acceptable. So you can see it basically matches, which means our simulation, in that aspect at least, is reliable. If that was any more than like e to the minus 2, so any bigger than that, you'd probably have some questions as to how good your simulation was, unless, of course, there's airflow going in other places, like inside a radiator or inside any other like leakages, basically. But if it's just inlet and outlet, those two have to match. So make sure that matches. And the last thing I'm going to show you is the actual pretty colored pictures you can make from CFD to see where the downforce is being created, where the pressure is, where you could improve any surfaces. And so we'll do that. If we go to open up graphics, double click contours, and then this window comes up. Now, let's say we want the contour of the symmetry plane in the rear wing. So we'll click symmetry. We'll make the coloring banded. And let's untick global range because we don't want all of the pressure. We just want the pressures within this symmetry plane. And let's do contours of pressure. Yeah, static pressure. We can do pressure coefficient. It's easier to read because it has smaller numbers. And let's do save display. If you then open up the graphics window, you will see this. It's going to look quite dark at the beginning. For some reason, Fluent adds some lighting to it. So if you want to remove that, go to View and uncheck the lighting. Now the colors look much better. And then drag that back up here and we'll zoom out. So to do that, if we grab the zoom tool and then click and drag, zoom out. And there we go. That is our pressure contour around the midplane of our rear wing. It looks quite good. You have that bubble of low pressure, negative pressure, in fact, you can see on this scale. We have a maximum negative pressure of minus 3.1. That's a pressure coefficient, that is. And obviously we have almost stagnation pressure up here, which means resultantly high pressure, low pressure, the wing is being pushed downwards, which is exactly what we want. We can also check, instead of the pressure contour, we could check the velocity. So if we just click velocity there and then save display, same thing will pop up, except with velocity now. So you can see flow is accelerating significantly underneath and slowing down above, which is what's creating that pressure gradient. And you can see we're at 45 meters per second below. The green obviously going to be our static, like our atmospheric velocity, so that's 22. And up here, the blue is next to 0. So again, that's a very good sign. We know our rear wing is working as it should. Velocity is also very good for finding, separation at the trailing edge of elements. We have a gurney flap there, which you can see if I go ahead and zoom into that gurney flap. You can see that flow is being separated because of that gurney flap, but that's expected. That's not necessarily a bad thing with a gurney flap. That is always expected. But yeah, so that's another thing you can check. Let's just zoom out again. There we go. And drag it back into the middle. Okay. So those are two kinds of, those are both flat contours. They're just two symmetry. There's just a symmetry plane that we were painting with pretty colors. We can also check the pressure on the actual surface of the wing itself. So if we go back to pressure and pressure coefficient, instead of drawing it on the symmetry, if we untick symmetry, we can actually draw it on the rear wing itself. So let's go ahead and select all of our rear wing elements and save display, and you'll see what happens. There we go. So now we have the actual wing itself. If we rotate it, you'll see the actual wing itself is colored in the colors that we want. Let's try and rotate. There we go. So you can see the top, all of it is red, and the bottom you'll see is blue. And this view right here is really helpful in seeing where on the rear wing you're gaining / losing performance, right? So you can see the edge closer to the end plate actually has more negative pressure, therefore it's producing more downforce than the middle, where the flow is being separated a bit right up here, where the third element is. So that'll tell you that you may want to back off the wing in the middle, or may tell you that you want to reduce gurney flap in the middle, maybe reduce the whole gurney flap as a whole. You may want to have some sort of swept profile for the wing, which gets quite complicated. And then the end plate here is also showing this is most likely a vortex, this kind of shape right here, coming off the tip. Well, we know it is because that's how end plates work. But this right here is showing you that a vortex is being created on the edge of that end plate and it's flowing backwards. So lots of things you can view with this kind of post-processing of the solution. Those are kind of the main ones. I guess another one I'll show you is if we go ahead and close contours and instead open vectors, double click on vectors. We'll color vectors of velocity and we'll do it on the symmetry, and you'll see what happens by delete global range, save display, and it's going to look quite small. Scale it up, and instead of 3D arrow, we'll just make it a normal arrow. Save display, and we'll go for the Z plane. There we go. So you can click any directions on this little compass down here, and it'll switch the view to that direction. And now, if I zoom into the middle, you'll see these aren't actually colors, they're arrows. So if I zoom in all the way right in there, you can actually see at every point in the flow or in the mesh which direction the flow is going with what velocity based on the color and the size. And yeah, you see obviously slows down here. There's a stagnation point right there, very expected. It's speeding up and following the curvature of the wing right there, again, expected. And if we drag it along, you'll see it still follows the curvature of the airfoil, which is very, very good. Then you have feed in of the high velocity air in there, which re-energizes that flow. So it sticks all the way up to the second boundary layer, second airfoil, sorry. And then if we look at the gurney flap, which is probably one of the more interesting points, if we move this and then go ahead and zoom into that gurney flap, you see the airflow kind of goes everywhere at this point, right? It's no longer just following the curvature of the airfoil all the way to the end, but it's now some of it's turning back very, very slowly, creating a little vortex back here. There's definitely a vortex there, which is the goal of the gurney flap, create that high pressure region there. And overall, it gives you a better idea of how the flow is behaving. And you can see that sort of vortex up here, vortex here. And this right here is a great view for the gurney flap because this is exactly how gurney flap is intended to work, right? The airflow comes up here, curves back round, comes up here, curves back round, and you get a higher pressure around here, which increases downforce and helps to keep that airflow attached for as long as possible. So that's just another tool you can use to visualize the flow. And there's many others, but I'll let you explore those for yourselves. Another good one will be the path lines. So you can see where the airflow is going. Instead of disjointed arrows, you can actually see path lines that go from inlet to outlet. You can also get different kinds of contours. So if I double click here and contour again, there's loads of different options that you can click on to see. And then, yeah, everything else is up to you, really. Once you've visualized the flow in the way that you want, you can then make improvements to your geometry, simulate it again, and then see if your improvements have made the correct steps forward. But that's going to be it. The last thing you're going to want to do is File, Write, Case and Data. So after solving, the solver creates a new file, which is a data file, and it is associated with the case that you solved. So if you write case and data together, it'll name both of them with the same name so that they can easily be opened in any other instance of ANSYS without hassle. So if you click case and data, name it whatever you want. We'll put it in this folder. Let's name it. We named this one before solved, so let's just name it solved. And hit OK. And then it's going to create, I'll show you, two files, one which is .cas and one which is .dat, which is a data file. The data file is the big one, the heavy one. So that's going to be all of your solution information, especially because we have a large mesh. We had quite a few iterations. It's going to be fairly heavy. But those will be forever associated because they have the same name. So next time you're in ANSYS trying to, say, open up an old simulation, you can just go to File, Read, and then go to Case and Data, and then select that name right there that we just saved it as, and it'll open up both with the solution already intact. And that's going to be about it. Once this finishes saving, there we go, done. So once it finishes saving, you can then close out of Fluent and go back to your workbench and save that as well. But at this point, the workbench is no longer necessary. You really only need Fluent from now because all of the files are within Fluent. And that's, I guess, the beauty, but also the curse of Fluent. It's kind of a bit separate to Workbench. It doesn't really use Workbench effectively, in my opinion. But it has its own files. So if you just have Fluent open, you can open whatever you want. I will say any 3D simulation shouldn't be run on a regular laptop. I think that's going to be very, very difficult for it to solve. Aside from the student mesh count limit, it's just going to be really, really time consuming and will really destroy the CPU on your laptop for a few hours. So I'd recommend doing it on either the HyTech computer or Pace if that's available. And the scripting is a whole other thing, which I've left a bunch of notes for. But yeah, that's it.